Well, let me stress that this is a kind of very informal added contribution. It will be rather technical about mode coupling equations, how to get them and what are some problems and so. So if you're not interested, please feel free to just leave the room and relax. Well, it's also kind of an ongoing thing, so I'd really appreciate discussion remarks and so on. Good. Let me show you how one can obtain mode coupling equations for FPU type equations and the like. So start from the fluctuating Burgers equation we have seen already several times, where phi RT describes a density fluctuation at position r and time t. And then there is a diffusive term. Oh, okay. Diffusive term, a nonlinear term, and the divergence of a fluctuating current, so GLs for Langevin. And this can be used for describing ASAPs and several types of systems. One can Fourier transform this equation, so ddt phi of k and t, and now the nonlinear term becomes a convolution product, and from a finite system you get a sum over k values, q values fitting on the system and this term. And now this may be rewritten in the form of an integral equation where you, well, this term and this term describe a homogeneous linear equation, and then these two are considered as nonlinear contributions. Well, the solution of the homogeneous equation gives you this, and the other terms give you that, and you see that you get a product of two phi's sitting here, and you can use this as the starting point for an iteration. So you take this expression and you insert it for either of the phi's, and you get terms with three phi's, and you go on and forth. And now it's very convenient to make a diagrammatic expansion for this. Yeah, you could say it's a perturbation expansion, where horizontal or curved lines represent these diffusive propagators. Vertices represent these factors sitting here, including sum of q and some integrals. Dots are used for initial values of the fluctuations, and asterisks for the fluctuating currents plus some integral over it. So, well, the simplest diagrams are then, well, this one, and then the fluctuating current one gives you this. And the first iteration, if you insert the first two terms, give you this one, where you insert this one for both of the branches here. And then there are things with one thing going to a phi and one thing to a fluctuating current. And finally, there's one which goes to, well, product containing two fluctuating currents. You can iterate it again. You get diagrams like this, where you get now two branchings and several things. And now notice that you get terms with, well, two fluctuating currents for different values of the wave numbers, and one is this. But now this can be simplified by using properties of the fluctuating current, which can, well, I'll assume that this can be represented by Gaussian white noise, with variance given in Fourier representation. Well, the expectation value of the product of two of these currents will be a delta function of q plus q prime, so q prime has to be minus q to get something, and a delta function of t minus 2 prime. This is still for arbitrary dimensions, so this is a, well, a d by d unit tensor, d dimension. And as of q is the static correlation function at the initial time. Now, assuming that the endpoint equal time density correlation functions may be factorized into products of two-point correlation functions, that is as exact when you have Gaussian statistics And it will be the dominant contribution, even in the case that you don't have Gaussian statistics. You say, well, okay, the correlations of, say, excitations, well, 4 correlations is, you get a maximal contribution if you get 2 correlated here and 2 correlated anywhere else, but you don't care about these different positions. That gives you much more than when you require 4 different ones to be correlated near the same point. But there are many more of those, so there's a tricky point to that. And then you can use this to make contractions. So, for example, here you look for, well, diagrams which have opposite values, like Q minus K and K minus Q, and you combine that with a diagram where you have Q minus K acting upon a fluctuating current K minus Q on a fluctuating current, and you can use that. Well, this gives a density correlation function at the initial time, and that's then multiplied with this e to the minus dk squared stuff. If you combine it with this, you shift the density correlation function to this time point, and you can do the same with other diagrams. And then you can say, all right, we define a right vertex as the density correlation function at this time, okay, times this stuff. Let's see, there should be some stuff in between. Or did I? Let's see. Well, I lost some transparencies, but okay, if you do this, and you do it in a systematic way, you find you get all kinds of diagrams where you get these branchings, and you get more branchings, and you get combinations. See, then this goes on, this combines to that. And then you end up with this, and you get this branching again, it combines, and you get a Dyson type of structure. And the self-energy diagram, so it's the sum, well, this bubble diagram is the sum of all the diagrams you can construct by branches to the right and to the left, and branches to the right. And the simplest approximation to that, well, you can do resummations, you add all kind of stuff in the middle. You say, all right, this is the full propagator, which is the sum of all of this. And then the simplest approximation is that you say, you branch into 2 of these things, this comes together, and this comes here. And so this approximation to this self-energy diagram gives you the simplest mode coupling equations, which are often presented as the mode coupling equations. But of course, this is only a first approximation, because you can add all kinds of things in between. And in high dimensions, you can show that these more complicated diagrams will be, say, faster decaying in time than the simplest one. But in 1 dimension, you in principle have to keep them all, because they will all contribute to the same leading orders. Good. Now, this was for the Burgers equation. But now let's go to fluctuating hydrodynamics. Here are the hydrodynamics equation. This is the continuity equation. What remains of the Navier-Stokes equation in 1 dimension. There is no shear viscosity, but there is a block viscosity. And then I add the derivative divergence of a fluctuating stress tensor. And the heat equation is written as, well, an equation for the entropy density. But the entropy density is really defined in terms of energy density and deviation of the number density. So here is an example for the pressure. The PdX is defined as the PdE at constant n, the EdX, plus the PdN at constant E, the n dx, and the same for the time derivatives. So that assumes this form. There's a nonlinearity, there is Fourier's law, and there is also a fluctuating current. And now you can linearize these equations, and well, you're left with these equations, just linear time derivatives, and these can be diagonalized. And so this P and this T are linear combinations of N and S, if you like. And if you do that, you get three hydrodynamic modes, discussed at length by Herbert in his talks, two sound modes of opposite direction, and a heat mode which describes the heat transport and, say, the decay of oscillating heat disturbances of your system. And you can expand the nonlinearities to quadratic order, and you're left with nonlinear hydrodynamic modes satisfying to leading order nonlinear equations to quadratic order. This is just like the fluctuating Burgers equation, except that, well, there is, say, a decay rate which can be partly, say, propagating. For the sound modes, there is minus I omega k, where omega k is sigma is sound velocity times k, minus k squared times, well, sound mode damping constant, gamma over 2. For the heat mode, this would be 0, and this would be the heat diffusion coefficient. But in principle, you can couple the amplitude of any mode to the product of amplitudes of any other mode with coupling constants, of which you have, in principle, 27 numbers. But many of them do vanish. And then you can make a diagrammatic expansion again, but now your propagators have to be specified, whether it's a propagator of sound mode or, well, this would be the heat mode, and this would be plus or minus sound mode. And for the densities, you have to specify if it's the density of heat or, the amplitude of a sound mode. And you also have three types of fluctuating currents for the heat mode and for the two sound modes. And in this linear order, the heat mode just decays diffusively. The sound modes propagate and decay as well in a diffusive way. Then for these things, you can set up your diagrammatic expansion again, but now you have to specify which mode is coupled to which pair of modes. And and then you can look at correlation functions of these amplitudes, and they may be expressed as sum of all connecting diagrams consisting of line pieces and so far left vertices. And now we would like to make this simplification again, where we combine, say, elements of diagrams into right vertices. And now I have a problem, and I don't need the screen anymore. I'll work from here on the blackboard. And so I would like to see is that, say, I have a mode of type beta, that is wave number k minus q, and a mode alpha, mode gamma, a wave number q, and they combine into a mode alpha of wave number k. So the sum of these wave numbers always has to be conserved. Light would be helpful. I can do much. Yeah, thanks. Good, and the weight for this process is minus IKW alpha beta gamma. And I would like to get us from beta k plus q and mode gamma of minus q, gamma q. Gamma branching into alpha k and beta q minus k, plus this, okay. Q minus k, and then plus, similar thing, beta k minus q branching into gamma minus q alpha k, gamma q, plus, the same thing, ending up into beta k minus q gamma minus q, and here gamma q. And this would happen with minus I k minus q w beta to alpha gamma, and this, well, okay, same weight here. And now you see that for this to work, these w's have to be equal to each other. And then I can just add up this ik minus q w beta, and here I have, this has weight minus iq w gamma alpha beta, and I want to get minus ik w alpha beta gamma. So if all these w's are equal, that works, and otherwise it doesn't.
So the first diagram that means that the branching of the end with the cross?
No, this one ends at an asterisk.
The first one?
The first one, let's see, this ends at a dot. So what I use is this property that the integral 0 to t dt e to the minus 2d q squared t equals, well, 1 over dt prime t minus 1. And then this would just compensate the term which comes from, well, all right, it is the minus sign here, it's plus 1, minus 1, that. This would compensate the term coming from this one, and this would just get you to the static density correlation function at time t. That's the fluctuation dissipation theorem, which tells you that, okay, the decay of a product of these modes to the exponential decay is in the stationary state exactly cancelled by what is generated by the fluctuating forces. So it comes out very explicitly in this type of presentation. Good. So I want this, Herbert calls this a cyclicity condition, W alpha beta gamma equals W beta alpha gamma equals W gamma alpha beta. And now I do obtain this condition if the fluctuations are Gaussian distributed, multi-Gaussian. And I can show that. Look at the time derivative of A alpha q and t, A beta k, and t times A gamma of minus q minus k and t. The average of this in the stationary state. Of course, this has to vanish in a stationary state, because just because of stationarity, it must be time independent. But now if you work it out, you get, well, first of all, if you let the DDT act upon the A alpha, you get minus I nu alpha times A alpha, here minus I nu beta, here minus I nu gamma. So you get this minus I nu alpha. Let's see. Q plus nu beta k plus nu gamma of minus q minus k times this product of these three density fluctuations, expectation value. And then you get contributions from the nonlinear terms, which will be 1 over 2L, so the volume of the system, sum over wave numbers L. You get minus IQ W alpha and sum over modes delta zeta, a delta of L, a zeta of Q minus L. This is from the nonlinearity in the time derivative of the A alpha. This multiplied with L, a gamma of minus K minus Q, and you get a similar term, minus IK W K minus L alpha of Q and a gamma minus K minus Q, and finally minus plus I K plus Q W gamma delta zeta L, a zeta of minus K minus Q minus L alpha Q, a beta of K. Now, if you have Gaussian statistics, this works like a charm, because then the expectation value of a product of 3 will vanish, and the expectation values of products of 4 will factorize into products of 2. And for these products of 2 to not to vanish, you require that either equals delta equals beta. And let's see, this should not be an L, this should be K. Okay, so L should be minus K, and then this one contracts with that one. And the expectation value of a product of modes, if they're normalized, is just 1. So you just get, well, minus IQW alpha delta zeta. From this you get minus IKW beta delta zeta, and here you get plus IK plus QW gamma delta zeta. And that has to hold for each K and Q. And so you see it can only work if indeed all these W's are equal. But the problem now is that in hydrodynamics, as a rule, the expectation values of products of 3 mode amplitudes doesn't vanish. That's just thermodynamics, and there's not much to be done about, well, at least that's life. And now you get a similar type of identity telling that nu alpha Q plus W alpha delta zeta plus must be equal to, well, nu beta of K plus this term, plus possibly contributions for products of 4 of these things, because they need not factorize in that case. So in any case, you will not satisfy this cyclicity condition. And so you have a problem. Now, what can one do about it? And I've thought of, well, two possible solutions. The first possibility is to go to more microscopic formulation of mode coupling theory. Where and T would be E sum over all particles e to the minus ik xi at a time t. And so you can define energy densities and momentum densities, well, similar way, and linear combinations of those will establish the hydrodynamic modes. And your inner products are now defined by looking at well, expectation values of products of these in your phase space. And now, this is a very common way of looking at mode coupling theory. And you look at hydrodynamic modes, and you look at products of hydrodynamic modes and the space spanned by those. But now it is very reasonable to go to an orthogonal kind of frame. And that means if you look at products of modes, you have to subtract contributions along the, say, lower components. So if I look at A alpha of Q, A beta of K minus Q, I would have to subtract minus the sum over gamma A alpha, A beta, and the product is A gamma. Well, this Q, this at K minus Q. Then to get something, the wave number of this gamma has to be K times A gamma of K. And now, an important remark is that the norm of this subtracted term is smaller by 1 over the square root in volume than the term itself. So it's a tiny contribution, but it does have a big effect on some of these mode coupling amplitudes. And so you do the same with products of 3, products of 4, and always the leading term will be just the products of the modes, but there are these subtracted terms. And then you establish the mode coupling by looking at time derivatives of all these, and say the branching of a single mode is given by, well, the magnitude of A, say this is alpha K, this is beta Q, this is gamma of K minus Q, and you get W alpha beta gamma equals the expectation value of ddt t of A of K with A beta Q, A gamma K minus Q minus this subtracted term. And this is in fact also what you, well, to start with, because to determine the frequency of the modes alpha, you have to include the contribution of the current that is, well, the current that is along this mode. So also the contribution of the product of modes is included in there. Which doesn't tell you that this couldn't pop up again at later times. But then to get a right vertex, you look at the branching. So you have, say, a beta Q, a gamma K minus Q. Look at the time derivative of that, and look what is the component of that along alpha. And now, just because of stationarity, the time derivative of A beta, A gamma in a product with A alpha will be up to a minus sign, the same as the time derivative of A alpha along A beta, A gamma. So automatically you find that the right and the left vertices are identical. Well, up to this factor I, but because of, well, complex conjugation in the inner product, that minus sign drops out again. And this will also work for higher order terms because the dominant term always comes from the branching of one of these A's in products of these things. And so by using this version of mode coupling theory, you automatically get this symmetry between left and right vertices. And, well, you don't even use this cyclicity. And now, I tried to use this also at a level of fluctuating hydrodynamics, and I got stuck there. I got into a problem because I don't get rid of these terms involving fluctuating currents. And so I thought, all right, let's take products of modes and orthogonalize them, and I work with that. But then, well, what do I do with these things containing the fluctuating currents? In the mode coupling theory at the fluctuating hydrodynamics, you always get from, say, from 2 modes to 1 by branching to 3 modes and then contracting 2 of them. And that can be combined with products of fluctuating currents, and so that works neatly. So that doesn't work, but I found another tentative solution, and it looks good to me. And the idea is, well, if these modes do not satisfy this property that products of 3 vanish, let's redefine the modes a little bit so they do. And so the idea is that you define B alpha of K and T as A alpha of K and T plus some C, say alpha beta gamma, and Q A beta of Q, A gamma of K minus Q. And then let's see if we can define these coefficients in such a way that indeed expectation values of products of 3 can be made vanishing. And that's fairly simple. So you just take, well, A alpha, A beta, A gamma of different wave numbers. And, well, just simple algebra. If you use the approximate factorization of products of 4, you find you can satisfy that if you take C alpha beta gamma equals C beta alpha gamma equals C gamma alpha beta equals, well, 1 over L, so minus 1 over, well, 3L, because you get 3 times A alpha, A beta, A gamma. And now, what effect does this have? Well, okay, it changes, let's see, the norm of each of these contributions would be of order 1 over L smaller than this term. But, of course, the number you get of these increases as 1 over as the distance because the density of Q values is proportional to the size of the system. But then you can argue that, all right, for long times, you only need a restricted range of k values because everything else will decay rapidly. So at least if I go to long enough times, I can restrict this to a small enough set of q values that this is a small correction. You can rewrite the hydrodynamic equations in terms of these b's. And then you see that, okay, the first contributions come from these, and they won't change because they have the same A alphas. And then the ones you, rewriting A alpha as B alpha minus this stuff. And the next ones are of at least cubic order, and they are not relevant within this theory, so they won't change the equations very much. In addition, you have a small coefficient because this is 1 over L sitting here. So this looks like a good solution. In the thermodynamic limit, it won't change the equations at all, except you change these static correlation functions such that they have the desired property. And I think Herbert has proved that this is not only a necessary condition that is finishing for this thing to be Gaussian, but it's even sufficient. And so then you're really in good shape. And well, I hope this indeed will solve my problem, and I can present it as well, the way to do things. Okay, thanks for your attention.